First one, optical wireless communication, a brief introduction, then visible light communication system, then how to design a visible light communication system using OptiSystem. Then for this designing, we need to some parameter values to set the OptiSystem layout. So brief introduction about OptiSystem layout parameters, and after that implementation of visible light communication link using OptiSystem wavelet. So optical wireless communication. Optical wireless communication spectral band is between 300 gigahertz to 30,000 terahertz. That is wavelength between 1 millimeter to 10 nanometer of the electromagnetic spectrum, and covering the infrared, visible light, and ultraviolet light bands. So visible light communication applications which are in the visible light frequency band is ranging from 780 nanometer to 380 nanometers. So these are the different class of optical wireless communication. Here ultra short range where 100 centimeters range is chip communication level distance, and short range which is up to 1 meter range, we can use optical wireless communication. And medium range means vehicle to vehicle, vehicle to infrastructure communication, or visible light communication for wireless local area networks. These are range up to 1 kilometers indoor infrared instruction. Then long range up to 10 kilometers or more, use which is use free space optics. And in our mobile communication, they are used for basically for mobile backhaul system. Then ultra long range, more than 4,500 kilometers, that is the space communication between satellites and all the uh, long distance communication. So these are the different classes. We are going to see the how the VLC system, visible light communication system, is designed. So this is the optical wireless communication system block diagram. So we have to take input data, and this input data given to the channel encoder. Channel After channel encoder, we have to give the modulator and signal up to here in electrical form, and that signal is given to the optical transmitter that convert the electrical signal into optical signal. And this optical transmitter may be LED laser type of source which can transmit the data in form of light. So we have one channel or one medium, that is a free space link, which is maybe uh, free space of space or in a room environment, air environment, like that. So here we transmit our data in form of light, and this data or this information can be influenced by ambient light. Here ambient light is, or outside light is, just like a noise for our transmitted data. And this data is received by a optical receiver like a photo detector, and that convert the optical signal into a electrical signal. And again we demodulate that signal into a particular format, and again channel decoder decode the information bit, and we get the finally output data. So whole system is a optical wireless communication system. If we are using here a free space link in a room, means 3 meter by 3 meter or more than 3 meter by 5 meter, so it is known as a visible light communication. Means one LED is there or one laser is there which give the light as well as used for the transmission of data. Or we can use it as a top of the buildings for long distance, for communicate the long distance. So that is a free space optics, known as free space optics, that is more affected by the atmosphere turbulence and different type of atmosphere uh, parameters. So this is the whole electromagnetic spectrum, which is quantified using wavelengths. And here we are going to use only a visible light area, visible light communication. We use only visible light. So this range is from 350 to 700, or we can say that it is 350 to 780 nanometers. So between this we use this much of the communication wavelength for the communication. Now come to the visible light communication propagation model. So visible light communication constitutes optical links which enable visible light sources to be employed for transmission of data using air as the transmission medium. So here our data is in a binary form or digital form, that is 0 1, and we transmit into the module through the transmitter, and one channel block is there. Data will transmit to the channel block with the help of LED, and receiver side it receive with the help of photodetector. So this is the complete propagation model. Here first data convert into a appropriate format with the help of a modulator and amplify that signal, and that signal is to transmit to the channel. So for optical communication we need only positive signal. We can't transmit a negative signal with the help of LED or transmit or laser. So we use some DC biasing to get the only positive signal. So with the help of this DC biasing, we convert this our signal into a positive format and then transmit with the help of LED or laser. In the channel, um, so many parameters that affect the transmission, that is the fading, shadowing, and ambient lights. So some parameters add up in our signal, and some parameter reduce our signals format. Then our signal is received by a photodetector. Between that we have to concentrate all the light signal into a particular photodetector. So we need a concentrator, and we use a blue filter to reduce the yellow light effect, because yellow light reduce the speed of the communication. So we just here use blue filter to reduce the that effect. Now photodetector convert the optical signal into electrical signal, and that electrical signal is amplified, and at the receivers again some noise and thermal noise, flicker noise, and photonic noise are there. Then that signal again amplified and processing. After that, using analog filter, we get the our output signal, and demodulate that signal, we get the finally transmitted signal in the form of our input signal. So this is the whole propagation model. In this session we are going to just see how this input signal convert into the optical signal, and how we trans and receive at the receiver side, which type of modulator and which type of amplifier we are going to use. This is I am not going to discuss here. I'm just simply design a link, means that is the input signal, light source, and photodetector, and how the signal is recover. So this is the block diagram link, visible communication link using LED. So here our input data, we are going to encode that data into the non-return to zero format, and up to here this point, this second block output is the electrical signal, and this electrical signal is converted into optical signal with the help of LED, and this is the VLC channel. This is nothing but a room environment, room temperature, uh, and simple air atmospheric channels. And this is the this signal is received by photodiode, and this photodiode is then passing through the uh, simple analog filter. Output of the photodiode is passing through the simple analog filter, and that analog filter is uh, generate the output data. So design for the indoor VLC link using OptiSystem 19. So this is our design diagram for today's session. So here we are using pseudo random generator sequence which generate the binary data, then pulse generator, and this is given to a LED which generate the optical signal equivalent to electrical signal, and this is our channel, and designing parameters are these. And after that this signal is received at the receiver side, and this signal is passed through a analog filter which can be a simple low pass rectangular filter or Bessel's filter or any type of filter, and we can visualize the signal, how its signal is seen, and how was the bit error rate of the system. So before that we have to learn about the some parameters which is useful to set up the layout. So brief introduction about OptiSystem layout parameters here, which is also known as global parameter or layout parameters. So this parameters is for new design. You must first define your global simulation parameters. So these parameters are critical to the simulation as they will affect the speed, accuracy, and memory requirements for a particular simulation. And global parameters also have an impact on all the components that use these parameters. So if you are going to, when you are going to use OptiSystem and you open a new layout, so and a blank at the blank in your layout, just click a right click, you are just open the layout parameters. So these window is picture is taken from that window, that is the simulation parameter, first simulation parameters, then signal parameters, then spatial effects parameter, noise parameters, and signal tracing parameters. So one by one we let's we see how these parameters affect and how we have to set this parameter for any type of simulation in OptiSystem. So first one, simulation parameters. So define the primary setting for your simulation. The three most critical parameters are bitrate, sequence length, and the sample per bit. So bitrate, sample length, and samples per bit. So these parameters you have to define first, and sequence length and sample per bits are always set to be 2 to the power, because these are use FFT system. So for good result we have to set this parameter values in a 2 to the power n. So like a sample per bit here, it is set as 32, means 2 to the power 5, and you can set like that. And sequence length also 1024 bits, means again 2 to the power 10. So like that you have to set all these parameters. So some tips to assist in setting up the simulations parameter. First one, set the bit rate to the fundamental binary data for your simulation. Means, for example, if designing a WDM, means wavelength division multiplexing system with channel operating at 10 gigabits per second using on and off keying. So set the global parameter bit rate to 10 Gbps. If you are setting different data rates, then it going to be used in a simulation. So associated bit sequence generators can be used to locally adjust the binary data rate or as a ratio of the bit rate or directly defined. So we can define directly, but if you can use the set through the layout parameters, then it will be good. The sequence length should be set based on the simulation objectives. So use long sequences if you need to gather statistical metrics such as eye diagram or bit error rates. Otherwise, use short sequences to study the optical effects such like a pulse dispersion. So sequence length setting is depend upon that, and if sequence length is more, then your simulation timing is also more. So based on that you can set which length, how much the sequence length, and based on the how your what is your project and what is you are going to calculate. Then the samples per bit parameter along with the bit rate and the sequence length directly affect the sampling rate of the simulation. So once the sequence length and bit rate are set, use the samples per bit parameter to fine tune the resolution of your simulation. So with the help of this parameter, you easily find your outputs. Then set the symbol rate to the fundamental symbol data rate of your simulation if designing a higher order modulation system. So bandwidth of cutoff frequency of most electrical filter are linked by default to the symbol rate. So for example, if designing a pulse amplitude modulation for PAM4 modulation system with a fundamental bit rate of 10 Gbps. So set the symbol rate like a 5 Gbps. So in this way you can set the simulations parameters, and these are really helpful to give you the good output or fine output. Then next one is the signal parameters. This is the first one is the iterations, means number of signal blocks generated by each simulation. It mainly affects the transmitter and component used in the bidirectional simulation and in network rings designs. So normally it is defined as 1 by default. You can change according your applications and your requirements. Next one is initial delay. This parameter forces a component to generate a null signal at each output port. It affects all component and it is mainly used in bidirectional simulations. So if your simulations is bidirectional, so this is the important one. Parameterized signal parameter is define whether the signal output will be sampled signal, disabled, or parameterized signals. It can affect components such as optical sources and optical pulse generators. And last one is the synchronizes, that is define whether bitrate will reach calculated in order to make sure that the number of samples and the number of bits are both power of two numbers. It can affect components such as pulse generator, decoder, and bit error rate analyzer. So it forces compatibility mode with the previous version of OptiSystem 7. So these are the parameters of signals parameters. Next one is the noise parameters. Convert noise beings and select whether noise within a sampled band's frequency range is added to the sampled signal or represented separately as noise beings. The default value is disabled, which means the noise propagate is separated from the signals. It can affect the iridium doped fiber amplifier and photodetectors. So if you're going to use such type of amplifier or some photo detector, so you have to set or reset this parameters for the noise parameters. Next one is the next and last the spatial effect parameters. The spatial effect parameters affect the components that generate spatial model where the discretization space and the level of the discretization should be defined. The number of points per spatial model is defined as the product of the number of points in the x and y coordinates. So the space width divided by the grid spacing give the number of points in x or y coordinates. So this is the space width and this is the grid width, and depend upon division ratio you can calculate the we can get the spatial effect the parameter. And last one is the signal tracing parameters. OptiSystem allows for fast estimation of power and noise at each output port. This estimation is calculated every time a signal is sent to the component output port. So the signal tracing parameter allow the user to control the calculation and presentation of the results. So these are so long number of parameters is there in this section, means signal tracing section. So if you are going to calculate signal tracing, so it define it's the signal will be traced. Then power unit says that the units used to display the results in dBm, in watt or milliwatt. Then frequency unit, the unit is used to display the results in hertz, in milli or in meter, in terahertz or in nanometers. In decibel places, the number of decibel places to use when the display of the results. Sensitivity, the minimum output power that the calculation can detect. And resolution, the spectral resolution bandwidth of the calculation. And calculate noise floor, defines if the noise floor will be calculated using interpolation, or this is an important parameter when the noise is added to the signal. Now next is the interpolation offset. The interpolation offset from the signal channel center frequency used to estimate the noise floor. So these are all the layout parameters which have to be set or keep as a by default, depending upon our project how much it is going to affect our designing system. So let's go for the implementation of visible light communication link using OptiSystem. So this is the OptiSystem software, and this is the layout, and this system is we are going to design here. So I am going from the starting. So go for the file and take a new system. This is the blank layout, or just like say is a layout one, you can rename it here. And these are the component library. So by clicking here at default section, you can convert into this format, and you can see that from here uh, by each section having different components. So here we can use transmitter library, optical fiber library, amplifier, and so much components is here. Depending upon our system or our design, we can use this. Now come to the layout one. Here, just right click, and you can see the how is the option is available. So the first one is the here are the live layout property. Click on that, and you can rename that layout properties whatever you want to know, or whatever you want to just reflect. So for example, VLC communication, now it is reflecting as VLC communication. Now if you are going to double click on that, so you are getting the so this is your all the parameters what we are discussing just now, and this is the simulation parameters and signal, spatial, noise, and signal tracing. So here bitrate is by default 10 Gbps is set it. If you want to change in the time window and sample rate, so you can go for here and you can set the option based on that, and sample per bits based on that you can set. Just like if we want to set this is the 64, 64, so you can set like that. So this is the simple parameter setting. Based on that you can set all these things. So for our simple designing, we need to just set the sample per bits, and we can set this bit rate up to 1 Gbps and set OK. Now, if you are going component library, just right click in free space, you are getting the find components, and find components you can type. your component name if you are aware of the component in the OptiSystem, so you can easily find out your particular components. So as we are going to design a simple uh, PLC link, so first component is our digital data generator system or digital data. So that is generated by pseudo random bit sequence generator. So by here typings, you are just type one word or complete word, you just getting the component's name and component library folder here. So just clicking on pseudo random, double click, then you are getting into the that particular library, that is the bit sequence generator, and you are having different type of sequence generator like pseudo random bit sequence generator and user defined bit sequence generator and complication test pattern. So just drag it into our layout and this will be reflected here. Now each component has property and you can set based on that. So if you're going to in this property means double click on that particular component, you are getting that bit rate. So here it is by default setting as a script, and script is equals to bit rate. This means this is directly connected to your layout parameters. For example, whatever the value of our layout parameters here, bitrate 1 Gbps, it will be automatically taken by this pseudo random bit sequence generator. And if you are going to change this script into normal value or swift value, then it will be changed accordingly. So if you are going to normal value, so it will be 2.5 Gbps. So this is the main advantage of layout parameter setting. If you're set there, then you need not to set random frequently here to generate the pseudo random bit sequence generator. So this is the first part of or first component of our link. Second one is the non-return to zero pulse generator. So just again type find component nrz and enter. You are getting nrz pulse generator, sequence generator, and so just click on pulse generator. So these are the different type of pulse generators. We are going to use nrz, or you can use anyone depending upon your application. So simply just you put here. If your automatic connection is enabled, then it connect automatically, otherwise you have to uh, connect through your cursor. So by the cursor, you can just connect these two links like that. So whatever your binary data is here, it is converted into the electrical signal. Here it is a format of 10, and here it is a format of non-return to zero pulse generator. So again, pulse generator having some properties. Now currently I am going to set as a by default. So let it be like that only. Okay. And next one is the after pulse generator we need a LED, or we have the source which convert this electrical signal into a optical signal. So just go here, and second way to find out the our component is that just click on particular optical system. So transmitter, optical sources, and optical sources you are getting here LED. So this is the second way you find out your component where it is available. So LED you have to keep here, and again connect that to the LED section. So if signal is in electrical format, it will be reflected by red color, and if the signal is in optical signal, so it is reflected as uh, sorry, it is in format of blue color. Now you going to change the property of LED. Here our visible light range is 350 nanometer to 700 nanometer. So we have to set accordingly the output frequency of this LED for the visible light. So just go this units and just click on nanometer range, and this is equal to 1552. So just change it to 550. I am going to use 550 nanometers, and electron life type I am going to use. So these all values are a practical value I am going using from one paper. So that's why I'm using this one. No other reason to use for these values. According your project, according your design, you can change what is the RC constant and what is the electron lifetime you use. And what is the bandwidth? So bandwidth again, nanometers range, nanometers, and I am going to set is 330. So in this way, my LED is ready for particular wavelength, that is the 550 nanometer, and bandwidth is 330 nanometer range, and with some other parameters. And next one is we going to use the FSO channel. So in OptiSystem, no other option for the VLC system. So we are just to change the FSO channel or FSO component into a VLC system. So just type VLC, or sorry, FSO, and FSO channel is there. So you are having FSO channel or optical wireless communication channel and Li-Fi channel. If you're going working on Li-Fi, you can use also. So here I am going to use FSO channel and connect this LED to this FSO channel. Now we have to change the all parameters of this FSO channel, because we are going to use a VLC. So VLC not in a range of 1 kilometer, is in a just 3 meter or maximum 4 meter. So we can use here 1 meter by changing the unit 1 meter, and attenuation per dB kilometer you can change accordingly. So it can be 10 dB per kilometer, like that. Additional losses, and then geometrical losses. If you are going to set the geometrical losses, then you can set the transmitter setting and receiver setting. Otherwise you can disable these all the values. So I am going to set the transmitter aperture diameter and beam divergence in milliradians. So for example, here, transmitter aperture parameter is 7 centimeter, and receiver aperture diameter is 1.5 centimeter, and beam divergence is 63.5, which is in degree, that is in a 1108.284 in milliradian. So same values I am going to set here. Once again, 7 and 1.5. 7 and 1.5, and this is and 108.284 milliradian per second. So transmitter aperture diameter means what, how the how the aperture diameter means LED diameter and total transmitter part, the light is emitted from there, and receiver is a capturing area means receiver aperture diameter where the light is incident on that, and based on that we are going to set this. So for VLC system we need this type of setting, so we are going to set this much of values. Next component is our photo detector or receiver. So we are going to use here pin diode, pin photodiode. So pin photodiode or other detector also available. Based on that you can use which one is useful for your project. I am using pin diode simply. So connect this pin diode and set the parameter of photodiode. So responsivity type means which type of material you are going to use for your diode, like silicon, germanium, arsenic, or user defined. User defined means you can write a script and you can define that this material is this parameter, and you can set up according to that. So yeah, I am going here using silicon. Okay, next parameter is filter, analog filter for electrical, filter out the electrical signal. So just right click, find out the component, then low pass filter. So these are the so many type of low pass filters. So just I take Bessel's filter and Gaussian optical filter, Mach Zehnder, and delay informator. So many filters and optical components is here. So we are going to use just optical filter, Bessel's optical filter, and connect this component to this. Okay, this is actually optical filter, so it cannot be connected with the electrical signal. So that's why it's reflecting cross section. So just delete it and go for the electrical optical low pass filter. Mm. So here low pass Bessel's filter. So these are so much different type of filters. So go for the low pass Bessel's filter. Now connect this signal, and cutoff frequency is the 0.75 into symbol rate. So we have to change this because we are setting at with the help of bit rate. So by default it is connected with symbol rate. You can change it bit rate, or you can remain as symbol rates. So if you are connecting as a symbol rates, so layout property here, the symbol rate is 10 giga or 10 gbps, so 10 gb symbols per second is there. So based on that it will take the 0.75% of that value, or you can set accordingly your system. So I can change this bit rate, and okay. So this will reflect it our calculation. Now calculation is based on this bit rate, that is the 1 gbps. So like that you can set your parameters and your requirements. You can change all the things. Now our signal generated from here and reach at the receiver here with the help of this channel, that is our VLC channel or visible light communication with the frequency or with the 550 nanometer. Now if you want to visualize the signals how it is look like, so you use and how what is the bit error rate, so use the visualizer. So first 3R 3R regenerator. This is nothing but useful for your bit error rate calculation. If you are going to use this 3R regenerator, so need not connect to the pseudo random and pulse generator to the output side. It is automatically take the value from this layout only. Now next one is the bit error rate, BER analyzer. Different type of analyzer is here. We are going to use BER analyzer, and first point is connected to the first one, second one is the second, third, like that. If this 3R generator, you are not using 3R generator, then first terminal is connected to the P pseudo random sequence generator, second terminal is connected to NRZ pulse generator, and third one is from here filter out. So like that, this is one of the means new things you can connect here directly with the help of 3R generator. Now oscilloscope visualizer, you can connect and see how your waveform is generated after the NRZ, and how it will be after the receiver side at the low pass filter. Now just save your project like a project 1 or my I'm saving like project 1 and save and run the system. So as the you are getting the message calculation finished, then cut this window and you are going ready to display your output. Just right click on that. This is your bit error analyzer. Q factor is 2.95 and minimum bit error rate is 0.001. If you are going to click here show eye diagram, it will be look like that. So this is very bad reception of the signal. You can improve with the help of different parameters like layout property. You can increase the sample per bit 256 and reduce the rate, and again run the system. So now this time your Q factor is increased to 5.4 and your bit error is 5.6 minus e to the power minus 14. So based on this you can vary your performance or your system performance, or you can modify your system. This visualizer show you the how the your bit sequence are transmitted. So just click here, zoom and take a small part. So it show you 1 0 format of your random pseudo random bit sequence generator format, which is generated by electrical signal generated by non return to 0 format. And at the output side after the filter, this is your complete signal. So again after filter, it is showing like that 10 format. And the signal, if you want to see only the signal format is this. What is the noise? So this much noise is there, and signal plus noise, all the signals and noises. So like that you can visualize your signal. Now this is the simple sequence or simple lines link. You can add noise here with the help of different parameters or different components. For example, I am going to add another light into our VLC system, because in a single room or in a single communication, we can't assume that our transmission is purely ideal. So there are always some factor or some noise is there. So here I am going to take a component. This is the white light source, and this white light source is used as a noise. And I am just disconnect this link. I am going to use splitter, power splitter 1 to 2, or which is convert 1 into 2 power same branches, or coupler. So here we need to add 2 power, so use coupler. Just a second. Okay, this is just a optical coupler. Power meter, optical coupler is there. Yeah, optical coupler. Just a wait, I'm finding out the component of optical coupler. Optical transmitter. Yeah, power combiner. That is known as power combiner. Power combiner you have to add here. Now connect this link to that one, and this is your main line or your data stream, and this is work as a noise. Now because noise also having some properties, so we have to change here. So again we are going to set at nanometer, and because our transmission is on 550, so I am going to change the 550 nanometer wavelength, and I am going to use average power. So I just connect the power spectral density option and set it is at 60 dB, 60 dBm, and run the signal. So this is calculation finished. So you are going to get this type of eye diagram, or Q factor is now this time 4.1. So due to this error, due to this additional noise, you are going a Q factor is reduced 4.211, and bit error is also reduced, and your eye diagram also not in a very good format. You can increase power from here or decrease from here, like if it is 120, and run the system. So here slight variation is there, just 4.14, last time 4.11, and small variations. So this type of noise you can add or you can define, and with the help of that you can visualize the your link. So this is the simple visual light communication link creation with the help of OptiSystem.